Okay, so we've been talking about, well, this idea of a vector field and what it means, and we understand that it's something rather complex to work with, but it is useful and important. I mean, we're talking about meteorological events, hurricanes, tornadoes, things like that. Clearly, those are important things that we would want to study that would be beneficial. And an idea of a vector field allows me to work with them. And so ultimately our goal is to be able to solve problems with vector fields. But in order to get there, we need to come up with some algebraic and I guess calculus-based tricks to actually work with a vector field. In order to do that, as I said in the last video, we're essentially going to go back to things we have done before. There's a reason we learn things in this class in the order that we do them. We're going to go back to things we've done before and combine several different ideas that we've done. And I'm actually going to space this out over, it's a couple of sections in your book. So we're going to space this out over a couple of videos, just like I would do in class, so we can kind of think about what we're doing and then expand on it. And we're going to talk about what's called a line integral. And if nothing else, it's an integral, which is, again, it makes sense that we're covering it in calculus. I would point out, I remember doing line integrals as a student myself. And I've mentioned before, especially for those of you who've been in other classes of mine, I didn't fully understand what an integral was and how it worked when I was a student, so it got confusing in Calc 2. This was actually the moment when I was like, okay, I really have no idea what an integral actually is anymore, because I don't even know what line integral means. Like, I'm taking the integral of a line, but it's three-dimensional, so it's a line in 3 dimensions, and somehow I can integrate that, and am I getting an area, or I don't actually know. And that's what we have to think about. I would point out, as far as the definition goes for this, we're going to work up to it based off of things we've already done in this class before, which means while this will be a new thing, it's really something that we've looked at before in this class. Here we're just going to kind of formally define it. But in order to get there, we need to recall some of the things we've done before. We had smooth parametrized curves, which we usually called C. Given by R of t, here we want to do this 3-dimensional because we're sticking with 3 dimensions. So we define them by component functions x of t, y of t, z of t. We usually had t go from A to B. And we said, just so we're clear, if I had a smooth parametrized curve, smooth meant 2 things. One, that it was twice continuously differentiable. So the second derivatives were continuous. And that the first derivatives were unequal to 0 for all t on the interior of my domain. The endpoints could be 0. But for the purposes of this, and we kind of mentioned this in the last video, it will get really tricky if the curves that I have in space start crossing over themselves. So we're also going to need our curves, in this case, to be simple. Which just means all the parametrizations are 1-to-1. So there's no overlap. The only potential place where I could have overlap on my curve is if the starting point and the ending point give the same value. So say if it's 3-dimensional, I could have a helix, which is 1-to-1, it never overlaps itself. But, well, I guess if we did my helix the way I did before from 0 to 6 pi, then it would overlap itself potentially, depending on how I looked at it. But if I restricted myself to, say, 0 to 2 pi, well, then it wouldn't overlap itself. So now, much like when we looked at these things before, we're going to have to think about what we mean. But say, in the case of just a circle, even if it's in R3, if I parameterize a circle, it's not going to overlap itself, but at the starting and ending point when I complete the circle it will, but we don't have to worry about that here. That won't cause a problem. So now I want to have a smooth, simple, parametrized curve C given by R of t, and I'm also going to need some function f of, well, we'll say x, y, z. With a domain d of f. And again, we're not actually defining anything here. This is just stuff we have done before that we want to put it all together now. And we're going to have the added stipulation that this parametrization R of t, this parametrized curve, lies entirely within the domain of this function here. And essentially the idea is, I have a function in space that's, say, defined everywhere. Say I get this surface right here. We've done this before. And then we said before when we were talking about, say, limits, if I want to find the limit of this multivariable function, this surface in space at a given point, one thing I can do is, I can look at paths, curves, that go through that point. And when we did that before, we said, if different paths give different limits, then the limit does not exist. If different paths give the same limit, that doesn't actually say anything unless I can show it's true for every path, which I can't. You all remember the two paths test. But the idea here is, before, I took a function defined, say, in all of R3, or all of R2, depending on, this is a three-dimensional surface, so it would be in R2 in this case. And then I would restrict myself to certain paths along that surface. We want to do the same thing here. I'm going to have a three-variable function, which of course again means it exists in 4D, so I can't really do that. But my domain is definitely in R3. And for the sake of argument, say it's defined on all of R3 for the purposes of this. This curve right here, this parametrized curve in space, has to exist entirely in that domain. Then I'm going to do exactly what we did before. I'm only going to look at the curve, because maybe looking at the whole surface, or the whole four-dimensional surface here, is too challenging. So I'm only going to look at some of those curves in space. And what we do is, we call that the pullback of a function of three variables by a parametrized curve in R3. And essentially, the function is defined everywhere in R3. I just pull it all back to the curve that I care about. I don't really like the name and the terminology there, but the principle, the idea, is one we have done before. So again, don't think this is new. It's stuff we've already seen before. I will also point out, since I'm talking about terminology here, we're going to be talking about line integrals. If you look these things up, sometimes they're also called path integrals, which is actually what they were called a lot more often when I learned them. My instructors use that. They're also called curve integrals because these are parametrized curves. And I think the assumption is if you call them a line integral, and you're like me as a student, you might tend to get confused and think you're only parametrizing a line or along a line, when our paths in space are generally not lines. So we go more with a path or a curve integral. All the terminology is interchangeable, so just be aware of that, especially if, as I know you do, you look these things up online to research them more. Okay, but now we have all of these different definitions and terminology and all of that. Now we actually want to put it together and get our definition. The pullback of a function. Let f be defined as above and c and r of t as above. And I'm writing it that way just because I'm going to get tired of writing out those long definitions as we get in class. So I have a 3-variable function defined on a domain D of f. I have a simple, smooth, parametrized curve defined by R of t, and the domain of R of t exists entirely in the domain of f. Now the part we care about, the new stuff, kind of. The pullback of f by R of t is the composition f composed with R, with a domain I which is equal to the interval a to b. And not surprisingly, f composed with R of t is just my regular composition, f of R of t, which in this case, since I know R of t is my parametrization, that just means f of x of t, y of t, z of t. And again, keep in mind, this is my parametrization, a vector function, but then I plug the component functions x, y, and z into my regular my 3-variable function f, where this is my x variable, that's my y variable, that's my z variable function. Z variable, my component functions become my variables x, y, and z. So, we're going to use this later. Suppose we have this. Let f of x, y, z equal xy plus yz, and let R of t equal the parametrization e to the t 2 plus t squared. So I have my 3-variable function defined on R3. I have my simple, smooth, parametrized curve R of t. If I want to find the pullback, f composed with R of t, that's just f of R of t, which by definition, I plug R of t in there, and I get xy, which will be et times 2 plus t, plus y, which is 2 plus t, times z, which is t squared. And I can certainly simplify that, but for the purposes of this, I'm not going to. But again, all I do is take my composition, my parametrization x, y, z, and plug it in there for x, y, and z. X, y plus y, z. X, y plus y, z. And again, the key distinction here being, this is my parametrization, this is my function, it's the value of all the points along this curve for that function. Again, it takes my whole function, this is 3-dimensional, this would actually be 4-dimensional, but it takes my entire function, and instead of giving me the whole function, it just gives me the curve in space that I care about. Okay. But now, I understand what the pullback is. We said ultimately my goal is to come up with something called a line integral or a path integral. And for that, we need more. Because, well, if I'm going to integrate, and now I'm talking about parametrizations, then I know I can occasionally have issues when parametrizing when I have different parametrizations. I have to come up with a nice way to integrate a parametrization. And in the past, we did that. We used the arc length parametrization, which worked out well for us. So just to quickly go over it again, to make sure we're clear. When we wanted to parametrize with the arc length parametrization, we defined the arc length function, which was s of t is equal to the integral from a to t of dr d sigma, as a goes from t to b. And then using the fundamental theorem of calculus, s prime of t, the derivative, is just ds dt, which is the magnitude of dr dt. That's all Calc 1. But now, well, I guess I can manipulate this. Here, I have ds dt is equal to the magnitude of dr dt, which tells me ds is equal to the magnitude of dr dt times dt. But then I know by definition the magnitude of dr dt is just r prime of t dt. And now, well, when we worked with the arc length function before in neat parametrizations, the ultimate goal of using the arc length function was to somehow find something that related S and T, because then I could do some substitution and manipulation and then solve my problems out. And it was really awful and messy. We're not going to do that here. But here, I don't get a relationship between an S and T per se. I get a relationship between ds and dt. The two differentials, the differential for ds and the differential dt. Which is good for me, because now I can define my line integral. So just to save a little space, let f, d of f, and c be as above. So all my standard conditions, function f, continuously variable function, defined on a domain d of f. C is a simple, smooth, parametrized curve given by r of t on the domain from a to b. T goes from a to b. And then I have my pullback and blah, 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 where this parametrization lives entirely in my domain. Then the line integral of f along C with respect to arc length is the integral along C. Keep in mind again, there's all this different notation we use for integrals. C there, path integral, line integral, curve integral. So just be aware. Of f of x, y, z, ds. And again, this is important. This is the line integral of f along C with respect to arc length, which is ds. And we never liked working with ds before because you have to do all the algebra to get the arc length parametrization, and it made everything really, really messy and awful. And a lot of times we couldn't actually solve those problems. But now, well, I know how to get f along C using my pullback. That is the integral of f of r of t. Just do my pull-up back there. But now this is with respect to t. This integral is with respect to s. I need a relationship between s and t, and in particular, the differential ds and the differential dt. But that's what I got right here from the arc length function, the fundamental theorem of calculus. So now ds is just r prime of t dt. And now again, my line integral is defined with respect to s, but when I'm going to actually solve it, I need limits. If this is with respect to t, my limits are just a and b. But now, this becomes an integral with respect to t, which I can actually solve, assuming the integral is easy enough, which is the goal here. And I can then simplify that. We can also write it as the integral from a to b of f of r of t, magnitude r prime of t dt. That wasn't written straight. There we go. And now I have a formula for my line integral. And there we go. One thing that I'm going to say, but I don't necessarily want to write out the theorem, which actually be a lemma, and kind of go from there. But there are a lot of parametrizations I could do. This is the line integral with respect to arc length, but as it turns out, there's a lemma. The proof is beyond what we're doing, and it's not necessarily going to here. But this definition of a line integral is independent of parametrization. What that means is, using my understanding of the arc length reparametrization and the arc length function, I get this relationship between ds and dt, which then allows me to write this particular line integral out in a nice form with respect to t that I can solve. But this will actually be true for any parametrization, even if it's not the arc length parametrization. Which means I actually could have tried to define this differently using a different parametrization, but I actually chose to use the arc length one because we had already done this work before, which gave me this relationship, which let me get to here. And now this will work for any line integral I want to solve with for any parametrization that I have, which is good. Right now, to do an example, to see how this works, or given the length of this video already, to do part of an example and leave the rest to you. Compute the line integral of f of xyz equals xy plus yz along the r of t given by 2 cosine t, 2 sine t, t. Here again, I don't want any potential overlap, so I'm going to go 0 to 2 pi. One circular coil of the helix. So then let's see. Well, if I want to find the line integral, first I need a pullback, f composed with r of t, which by definition is just f of r of t, which is f of, let's see, that's r of t, plug that into f. I get 2 cosine t, x, times y, which is 2 sine t, plus y, which is 2 sine t, times z, which is t, which I guess I can rewrite as f of 4 cosine t sine t plus 2t sine t. So now I have my function and my pullback that I need. I'm also going to need r prime of t, and in particular the magnitude. So r prime of t, we know is dr dt, which for us, if that's r, derivative of cosine is negative 2 sine t, 2 cosine t, 1. There's my dr dt, but then I need the magnitude of dr dt, which is the square root of, if I square that, 4 sine squared t plus 4 cosine squared t plus 1. We know the trick. Factor out the 4, it becomes 4 times sine squared plus cosine squared, which is 4 times 1, which is 4 plus 1, and that's root 5. Now I have all of this. Now I can actually set up my line integral. This one better. And I get the integral along C of f of xyz ds is equal to the integral along my curve. T is divided from 0 to 2 pi, 0 to 2 pi, of f, which I just said was 4 cosine t sine t plus 2t sine t times the magnitude of dr dt, which is root 5 dt. And now, I'm not going to bother to solve this out. I will leave you, just because this video is long enough and I still have more to do, I will leave this to you to solve out, but the root 5 is a constant, you can pull it out. Integrate this, it's a u substitution with sine and cosine. Integrate this, it's a product, so you're going to do an integration by parts one time. Get the integral here, and solve it out. And the point being, we have this multivariable function, we have this parametrization, I get the composition of those functions, I take r of t to get r prime of t, then I take the magnitude of that, throw it all in, and while it can look messy, the alternative was to try to solve this, and I don't know how to do that with respect to S. This gives me a nice way to do it. And even if it can be a little bit cumbersome to solve that out, that is still preferable to not being able to solve it at all. One other thing, and again, this is where maybe as a student, I tended to get confused. I understand, and again, I actually do stress here, this is a 3-variable function which lives in 4 dimensions, but I'm looking at the pullback and the parametrization which lives in R3, so I can at least visualize that. Geometrically, can I even think about what it is that's actually going on? Well, if I'm integrating something in R3, I at least understand, and because we've already done this, that the thing I'm integrating, if I integrate below that, I'll get a volume. But then, well, what if I only integrate along one curve there within that surface in R3? Then essentially, again, if I have a sheet of paper here, if I just draw a line, and I think about the entire volume there, but then I only care about that one particular line, well then instead of getting, say, a volume underneath that, I would actually get like an area, almost like a curtain, if you will. I cut off a slice in R3 that gives me what I care about. And again, that is not exactly what we are doing here, but at least as far as a way to kind of visualize what is going on here geometrically, that idea will at least maybe help to understand it. Instead of taking the volume of the entire surface, I find a path, and then the integral gives me everything below that path, which kind of gives me like a curtain or a sheet in space. It's also why, again, I wanted to be careful when defining this, because if I think about it that way, then if I have this as the thing I care about, a helix, once the helix starts doubling back on itself, once I pass 2 pi, well then my brain says geometrically that might cause a problem, because then I'll have like the part of the sheet below the lower part of the helix, and then I'll end up counting some of that again on the upper part of the helix when it overlaps. So that's why I want to be careful here. And again, just little things like that to ponder to maybe help you understand better what's going on. I think we've established algebraically I can understand what's going on reasonably well. Geometrically, my brain just doesn't work that way. And you people, your engineering brains, probably can visualize these things better than I can. The other thing, again, I would point out, which is not important now, but it will be, but we don't need to spend a lot of time on it now because it's something you've seen going all the way back to Calc 1, where occasionally my domain in Calc 1 for my function is not defined well. Maybe it's got a hole somewhere, maybe it's a piecewise defined function, and can I integrate that? Well, no, I can't. But then I can take my integral and break up my integral into smaller integrals along each continuous piece of my domain, and then the whole integral is equal to the sum of all the smaller integrals. If that worked before, then it should work now. And essentially the idea is, if I have some path here and then some path over here and all of that, well then maybe I'll call this C1 and this C2, and I can integrate as C1 goes from here to here, and then as C2 goes from here to here. If my paths overlap, maybe I might think about, well, breaking up that path along different places where they overlap. Maybe that'll work, maybe it won't. If I'm going to think about my path this way, as a C1 and a C2 and stuff like this, then I definitely want to make sure, I'm thinking about parametrizations after all, that I understand there's an orientation here. Because then, if I integrate along this path and then this path, well, if I integrate, say, going backwards, then maybe I'll call that negative C2 and negative C1 if I go in reverse. And then clearly there should be a relationship between the values of the integrals I get. And again, those ideas are all, we'll say Calc 1 and or Calc 2 type ideas, thinking geometrically. We want to take those now and just expand them to our parametrizations in R3. So I don't want to spend a half an hour kind of rehashing stuff you already know from Calc 1 and Calc 2. So I will leave it at this. Just think about that. If I integrate along this path, if I go backwards, I guess maybe it should be negative. Does that make sense? I don't know. Could I think about that? And that's kind of what we want to look at. Maybe my path is a little bit messed up, and maybe it's got corners there. The corners cause a problem. They did in Calc 1, so maybe they'll cause an issue here. So if my path has a corner, maybe break it up into multiple paths, and then integrate along each one individually. All these different ideas, we're just going to ponder as we go through this. Maybe sometimes it'll cause an issue, maybe it won't. If it doesn't cause an issue, hey, great, we're good. If it does cause an issue, can we come up with an algebraic trick? Hey, break it up into two paths and still solve the problem, or do we have to do something else? And again, this is the same standard trick we've used throughout the semester. Remember what we did before, look at it in a slightly new way, and sometimes it works, sometimes it doesn't, and we just kind of figure it out as we go along. I would also point out, if we think about, say, a tornado or a hurricane or something like that, maybe I could find the line integral along, say, one certain band of that hurricane or one loop of the tornado, if you will. But ultimately, if I think about it from a vector field perspective, is there a way to expand this idea of a line integral to encompass like everything all at once? So far, we've only looked at one path. Is there a way to expand it so I can look at the entire surface at the same time? All different ideas that we want to think about as we go through this and see if we can kind of see what's happening as it happens. We're going to expand on this type of thinking in the next section.